Welcome to the CRE lecture number 24. It's my great pleasure to introduce my colleague Dan Frey from MIT. He spent some time in Singapore and has been committed to design education for a long time. So today he will talk about design of experiments and their use for international development. Professor Dan Frey conducts research in engineering design theory and statistics. He has developed and analyzed an adaptive approach to robust design. He served as a founding co-director of the International Design Center at Singapore University of Technology and Design. He currently serves as a principal investigator of a USAID-funded program in Guatemala entitled Achieving Sustainable Partnership for Innovation, Research and Entrepreneurship. The project goal is to improve the links in Latin America between higher education and the economy. Professor Frey is also active in design pedagogy and is frequently involved in efforts to review and improve engineering education internationally. With that, Dan, welcome to the lecture, and I will hand over the mic to you.
Thanks so much for the kind invitation and introduction. I'm really intrigued by the title and the objectives of your collaborative here. So I hope you'll find my comments interesting. I think it could be hard for me to see when hands are raised. So I hope that if you have a question as we go along, or if you want to make a comment or ask me to restate something in another way, please just speak up. So I've been thinking a lot about experiments, and they have had a very important effect on the history of technological innovation. And one of the very first major efforts in this area, formally speaking, was an application of experiments to agriculture. And we know that before the 20th century, there were much more frequent famines than there are today. Agricultural productivity has improved a great deal, and it's become more consistent as well. And a lot of that had to do with a systematic effort to improve agriculture through experimentation. And the fellow on this slide, Sir Edward John Russell, ran a field station in the United Kingdom called Rothamsted. And he wrote in a 1926 paper about how he viewed field experiments. And he said that you're basically asking questions of nature. And he argued for an approach emphasizing simplicity, that you want to ask questions in a way that you are keeping it simple, and perhaps even asking only one question at a time. And typical of that approach, you see a table here from a paper in 1921 in which they were exploring the effect of ammonia as a fertilizer, putting it on a field. There's no ammonia, single ammonia, double and triple amounts, and you could see the effects on how much yield you were going to get in the grain. The annual decrement, that is, the first season might work out better, and then it might back off from there. And so you were looking for good yield and yield that was sustainable. And Sir Edward John Russell was emphasizing simplicity in the experiments. But soon after that, he had brought a statistician to his field station. And this fellow, R.A. Fisher, really began to think about the experiments in a different way. And already by 1926, he was publishing experiments more typical of his approach. And in the figure heading, you can even see he called them complex experiments, as if to emphasize the change in the approach. And what you see in this figure is literally the way that the fields would have been laid out in 2 dimensions. And if I focus your attention on, say, just a quadrant near the top and at the left, it's 3 cells high and 4 cells wide, and it includes different combinations. I see 1S early, 1M early, 2M early, 2S late. These are the different combinations of 3 factors at 2 levels each. There's 1 and 2, different amounts of ammonia, S and M, different chemical formulations, and early and late, describing different options for the timing of the application. And if you have 3 different factors, okay, so I'll continue. If you have 3 different factors at 2 levels each, then there are 8 distinct possible combinations of those. And all 8 of those are found in that first cell at the upper left. And all 8 of those are also found in the cell to the right of it and the one below that, and so on. And so what they're doing is randomizing in space the application of these different factorial arrangements and getting replicates across the field. And this was done in order to reduce the effects of some random variation on the estimates of the different effects. So if, for example, the field became dry and the moisture in the field was varying from north to south, then it would be a problem. It would reduce the precision of your estimates, but at least it wouldn't bias any particular consideration. It wouldn't bias toward 1 or 2 or M or S because of the randomization across the field. So this particular arrangement brought about quite substantial, roughly a factor of 2 improvement in the precision of effect estimation. And so it was considered a really important innovation in experimental design and application. Now, pretty soon after that new development in formalizing design of experiments as a field in statistics, it was picked up by engineers. And a new kind of methodology was developed called response surface methodology. And it was used by, at first, chemical engineers and later all different kinds of engineers to improve their processes and products and services, anything. And they did it through a phased approach. The first part of response surface methodology is called variable screening, in which you reduce the number of variables that you're dealing with down to just a handful of the most influential ones. Then steepest ascent, trying to move toward better regions in the space available to the designer. Fitting of polynomial models, that is, making some smooth approximation to the system's response, and then using those mathematical surrogates to do optimization. And let me say a little more about that. On this slide, you see a description of a paper by George Box, one of the pioneers in that field. And he called it Statistics as a Catalyst to Learning by the Scientific Method. And this would be a good paper to go through if you wanted to get practice using this methodology for yourself. Includes an extensive example of this little paper helicopter. So you can print out this screen, cut out that little blue device that is on the screen, make cuts along the dark lines, make folds along the dashed lines, and you would have a little paper helicopter. And usually we also put a little paper clip at the bottom to hold it together and to keep it upright. And then if you drop it, it'll twirl as it comes down. And George Box went ahead and optimized that particular helicopter, changing things like how long are the little wings, how long is the body, should you include a heavy or a light paper clip. And he started with a screening experiment, what is called a low resolution design. So that indication 2 to the 8 minus 4 means it's a 1/16th fraction of a much larger potential experiment. The Roman numeral IV tells you how it can either detect or will just simply confound different effects in the system. So a resolution 4 design will keep the main effects clear of interactions so that you can use it for screening. Then he did some steepest ascent, built a full factorial in just 4 of the factors, made this thing called a central composite design, and ultimately had improved the helicopter by about a factor of 2. But this, if I go through and count the total number of experiments needed, that's 248. And with the paper helicopters, it's not a problem because they're not expensive to build, and it doesn't take very long to get your data. But you can imagine if you were trying to build a new commercial airliner, you couldn't afford to build so many different variants. And so you'd either need to reduce the number of experiments or do more with computational simulations. But in any case, this illustrates, I think, very clearly an empirical approach to improving something through experiments. And here is the idea of fractional factorial experiments and their use in checking for curvature. So you start with a space of 3 factors, call them A, B, and C. And if they each have 2 levels, you could potentially explore every combination, which would be 8, which would be the 8 corners of the cube. But if you only could visit 4 corners instead of 8, if you're trying to save on resources, you might choose this fraction here, which is represented by big black dots. And that would have certain advantages in, well, projective properties are one of the important advantages, and effect estimation ability is another. And then if you did decide to run runs in the center, it would help you to decide whether you are close to an optimum or whether you needed to do some steepest ascent first. So if you run these center runs, then you might consider evaluating the following statistic, which was computed from your data. You'd look at the difference between the data runs at the corner and the runs in the center and take the absolute value of that, divide it by an estimate of the random variation at the replicates, and normalize it using the number of runs and compare it to the t statistic at whichever level of significance you chose. And you could decide whether the curvature existed, whether it was statistically significant. And they did decide that their first set of runs did not have significant curvature. So they went through a process of steepest ascent. So this shows a graphical depiction of steepest ascent in just 2 variables, and it came from George Box's paper. And here you see lines of constant performance. They represent a kind of mapping of the response surface. And if you've ever used a topographical map for hiking, you might be familiar with this idea. If you walk along one of these black, they look like ellipsoids here, you'd be staying at a constant altitude. And if you walked perpendicular to those ellipsoids, you'd be going up as quick as possible. So they started off in this little rectangle and moved off in a direction that appeared to most steeply improve the performance. And you see in the first step, they get quite a bit of improvement. In the second step, it improved a little bit more, but by the next step, you're going downhill again. And so at that point, not having a complete map of the territory, you would at least know that you went too far and you had to back up. And you'd make an estimate of where the best performance had been, and then you'd probably do some more experiments to see where the very peak is. And if you used a central composite design, you might do something like this. You see a 2 to the 3 full factorial. You try every single corner of this space if there are 3 dimensions. And then you'd run some center runs and also some axial runs. And the axial runs mean that only a single factor is changed compared to the middle. And you typically make the change a little bit more aggressively so that you move at least to some degree outside of the original box, depending on what your objectives are. And then you can build a second order polynomial with all the terms, a squared, ab, all the interactions, and so on. And that helps you to identify what are called stationary points. So you build this model, it includes an intercept, linear terms there by the vector b, x transpose b. That term would give you linear effects in each factor. And then that last one, x transpose bx, that is the second order polynomial term, where B is a matrix combining diagonal elements that tell you about curvature in each individual factor, and off-diagonal elements, it's symmetric, which tell you about interactions between pairs of factors. And you can compute a stationary point from that vector and matrix with the formula xs equals minus 1/2 B inverse times B, capital B inverse times lowercase b. And that gives you a point in the space of the input factors that is what's called stationary. Now, those stationary points could represent maxima or minima, but in some cases, they instead represent a saddle or a ridge. So there is some additional work that needs to be done to discriminate among those, but at least gives you a sense of where the very best point in that space is likely to be. And George Box in this paper included a figure that I consider very significant. He said, these statistical procedures shouldn't be used in isolation. You should use them as part of an iterative process and use different kinds of reasoning as you take data and you move using that data to make theories or models. You're engaged in induction. And statistical reasoning is principally about induction. But then once you have a theory or a model or a conjecture, you should work in the opposite way. You should ask, well, what would be the logical consequences of this model? And which are the consequences that I find useful or intriguing? And then you should test those consequences. Test them for internal consistency, test them for consistency with all the data that you have available, and then go get more data and continue to repeat and hopefully converge by that method on a good design and a good understanding of the design. So I've always believed in that. I thought it should be part of every lecture that touches on statistics. So that is all the comments I wanted to make on statistical methodology and its evolution over time and the state of the art at about the time that George Box wrote that paper. And I want to tell you a little bit about the work I've been doing with colleagues here at MIT and in Guatemala. And we have a program, we're considered the prime, and we have two organizations that work as subs on this grant. One of them is the Universidad del Valle de Guatemala, which is a very good quality university in Guatemala City, and also an organization called Ag Export. They're a private sector partner focused on improving Guatemala's economy through exports. And what we're trying to do is through funding research projects, through pushing forward in education, making their courses even more hands-on and active, and very much along the lines of MIT's approach, mens et manus, and through innovation in the private sector by generating new ventures and new technology and licensing that technology. We're hoping to make improvements to Guatemala's economy and their prosperity and their communities by getting higher education more involved in not only educating, but also solving problems, creating new opportunities, and doing that all through engineering and innovation, and doing so in a participative way with community partners. Now, while doing this work, I was contacted by the USAID Guatemala mission. And the thing about that is that our funding comes from a bureau in Washington, D.C. But if you're in a country and you're working with USAID, you need to stay in contact with the mission, try to understand what their priorities are, and be responsive if you can be to concerns they raised. And they sent me an email saying they want to talk about research to determine what's working in their interventions. They have significant problems in Guatemala with poverty. And in particular, some of their mission partners are concerned with the nutrition that children are receiving. And it's thought that they're not getting enough food, maybe not the right types of food, and they may be experiencing problems like stunting of their growth because of that. And so they have challenges in that they can't tell which programs or which approaches are working best. They have spread out these interventions across geographies, across different types of recipients. And that has meant that some people are getting multiple interventions. And if they get a good outcome, you don't know really which one of the interventions is causally related to that good outcome. So they have a difficult epistemological problem as well as a difficult practical and design problem. And they asked me to try to help with that. So we put together a workshop, and we brought together actors from all different kinds of organizations, people from NGOs, non-governmental organizations that are trying to do work on addressing poverty, particularly child nutrition, people from the government who are doing work on statistics, trying to understand the effects of this work, people from the university, and, well, quite a diverse group of people. And we are very lucky to have them participating in our efforts. And so in workshop number 1, we focused on response surface methodology. I gave a talk to them quite similar to the one that I gave at the beginning of this talk, and in quite a bit more detail. I went into specifically how to analyze the data, how to organize experiments. We did examples with pieces of hardware. And then I also showed them alternatives, things that engineers do sometimes in a different style, one called Taguchi methodology and one that I developed myself, and also a fourth option called the MOST methodology. It is a version of response surface methodology that was really crafted to address challenges in behavioral and health interventions. And I had learned about this really just at the time coming up on the first workshop. And so let me say a little more about that. There's a book now available by Linda Collins, and she is a scholar working with a school of public health. Now she has moved to NYU, She had previously been in the south of the United States. And she wrote this book about how to use response surface methodology and related statistical techniques, specifically for behavioral and biobehavioral and biomedical interventions. But it was based on engineering approaches. And her methodology she describes in a flowchart. It starts with a preparation phase in which you really try to understand what is being done currently. And it is focused on this thing they call a conceptual model. You think about inputs and outputs of these interventions. You think about whether they're separable components of those interventions, and you try to state what your optimization objective is in clear and measurable terms. Then in the optimization phase, you actually do the experiments and analyze the data. You try to decide whether your intervention, now optimized, is effective enough. And if it is effective enough, you do some additional confirmation work. Usually that's a randomized control trial. But in some cases, it could be more traditional monitoring evaluation work. So this is how they describe the process. And once we decided to use the MOST method, we dedicated our effort in the third workshop to building a conceptual model. Now, here's an example of a conceptual model that was developed by Linda Collins for a particular intervention into child mistreatment. And so the intervention components that people have used in that area include training on parents in how best to raise their children, mentoring by peers, getting caring people involved, helping parents to do better, how to deal with conflict within the family, getting check-ins from professionals, things like that. And in this conceptual model, they make an important distinction between what they call proximal outcomes and distal outcomes. So this is important in health and behavioral interventions because these distal outcomes, like ultimately what you want is reduced child maltreatment, those may take so long to realize that you're not really able to perform effectively and optimize effectively unless you can find things that will act as surrogates. So they would look for things like improved parental engagement, something that you could observe much earlier. And if you can improve those proximal outcomes effectively through your intervention components, then perhaps you'd be satisfied and just defer your confirmation about distal outcomes until later, but do optimization on a faster loop. So we built a similar conceptual model of this process of complementary feeding. And in Guatemala, they're theorizing that children in these villages, they're getting breast milk when they're young, and up to about 32 months, in many cases, they're getting really more reliance on breast milk than would be healthy. They believe that long term, it would be better if children in a certain window from 6 months to about 3 years, if they would start to get some of the food from the usual table, maybe some eggs, perhaps a tortilla that's ripped up, something that would get them used to the foods that are available in the region, and introduce it, even if they're not getting very much nutrition from the solid foods, but get them used to it so that when the breast milk is no longer available, they make a smooth transition to normal feeding in that community. So this slide is mostly in Spanish, but we thought the proximal mediators or observable things would be frequency of feeding, introduction of solid foods by 6 months, and the diversity of the diet of the children. So we proposed some experiments that would have help them to decide whether their different intervention components are helpful in attaining those proximal observable behavior changes. But the problem is that when you power an experiment, when you decide how many different subjects you need, you are affected by the structure of the experiment. You design it as best you can for it to be efficient. You're dependent on the size of the effect you seek to detect. And if the effects are not going to be very large, you tend to need more subjects. It's affected by the variability in measurements, how precisely you can gauge the different things, the significance level that you have chosen, that is a risk that you accept of what's called type 1 error, that is concluding incorrectly that there's an effect when there isn't an effect. And ultimately, those determine, in power and experiment, usually you decide on the sample size in order to get some chosen level of power. As an example of how to do this, what you might do is take this thing called a nomogram and take the effect size standardized by the noise. And if the effect size were about 1, that is, if the effect size is comparable in size to your measurement error, and you wanted a power of 0.8, meaning that you want to be 80% sure that you see the effect through the experiment if it is present, then you draw a line between them, and at the different significance levels, like 0.05 is a pretty standard approach for type 1 error. And this nomogram crosses at a little above 30, so you need about 30 subjects to do the experiment. And we found that we could not get by with only 30 subjects because in social science experiments, often your power is negatively affected by this clustering that occurs in real scenarios. So if, for example, you're working on a health intervention, often a hospital is a natural cluster. Or if it's an educational intervention, the schools will be a natural cluster. And if the clusters are strongly correlated, that is, if one hospital gets good outcomes and the other hospital gets much worse outcomes, then you will need many more subjects in order to get adequate power. And so large numbers of clusters, small numbers of subjects within clusters, and high correlation of clusters are what really start to hurt you. And we had all those things. And so we recommended a study with 300 subjects. And they viewed that as too expensive to do this year anyway. And so we've put our plans on hold for the time being because it's going to be an expensive undertaking. And it's specifically because of these challenges of. So I decided that while we're waiting for more funding to potentially become available, I would give them some advice about how we might be. All right, so we wanted to do some cost benefit analysis to see if we might be able to justify a smaller experiment and to decide what is the right sample size for the circumstance that we're dealing with. And so we decided to choose a mathematical formulation, which is called a multi-arm bandit framework. And both of my collaborators there at IIT, Nandan and Anusha, they're quite knowledgeable about this approach. And you think of the scenario as a bank of slot machines. If you were faced with that situation, you might have only a fixed number of samples that you're allowed to make. And if you didn't know anything about these slot machines, some might pay out very well, and some might just take your money and give you nothing back. And so you might decide to do this in 2 different phases. One for exploration to decide which are the best machines, and one for exploitation to just pull the arms of the better machines. And you'd have to decide how much of your effort should be in the exploration phase versus the exploitation phase. And in exploring this, we wrote some theorems, and we found that the optimum number of samples in any particular stratum, which is like one of the slot machines, is given by the following formula. And that formula has a couple of terms in it, like an omega and an n. And the omega is a measurement of all the effect sizes linearly combined like that versus the error in your observations. And the capital N is the total number that you're able to take. And what we found, the bottom line in this paper was that your optimal sample should never be more than a third of the total. So if you are faced with this exploration, exploitation trade-off, you need to transition into actually doing the best intervention by the time you're a third of the way into your population. But you also never do no experiments. That if you do some experiments, you always get benefit from that. So the optimal sample size ranges. It depends on all these different factors that we were concerned with. But we can show you that if you know you're going to do an intervention, and if you can take at least some fraction of your total number of recipients and do it in a phase prior to full scale delivery, you would get considerable improvement. And we ran this on a PayPal case study. We had partners in the company named PayPal, and they were about to launch a new product in Australia. They knew they were going to roll it out to just 1,000 customers. And we called it a 2 to the 2 factorial scenario. There were some people that already had credit cards, some did not. Some people had this one particular risk factor, and some did not. So there were 4 different combinations. And we used their data to run a sort of thought experiment. And we were able to show that you would improve the profitability of the new launch by about 19% if you did the right amount of experiments. So we thought we were able to show something in a quite practical light. And so our conclusions overall were that the DOE is a really important field, and it puts you in a mindset of doing experiments to make things better rather than doing the same things over and over again. And those techniques, I find, can be adapted to almost any pursuit. And we think the international development community can benefit quite a bit from this kind of approach. And, we've held these workshops, we've shown them what methodologies are available, and we have not yet gotten to the point of doing really full-scale experiments with our partners. So I would say we're still at a very early stage in our efforts, but we think there's quite a bit of promise, and we're able to make some new insights because of our work with them already. So those are all the things that I wanted to say. Maybe I also give you my email address so that if you have questions that come up later, if you're sitting thinking about this tomorrow and you want to ask me a question, you'll be able to reach me.
Thank you very much, Dan, for not only a lovely lecture of how analytical methods, from statistics can be used to define the problem itself in the correct way and try interventions based on your current understanding of the problem. I think the latter part was very interesting to me from that point of view of your talk. And the other thing I wanted to mention is that there is some medical healthcare literature of experiments done in Bangladesh. It's called positive deviance. What they do is they take two adjoining villages, let us say. And in this particular case, the children in one village were relatively better in terms of malnutrition and other things, whereas the second village was not very good. When they analyzed the diet between the two, they found out that in one village they started giving tiny shrimps very early, food earlier, and that is what made the difference. So what they do is, like you pointed out, a peer group from both places to bring the mothers from one town and the other one, because they are adjacent, but they have slightly different cultural practices. So there is a potential for transferring the cultural practices from one to the other group. And that's what they did, and they had some positive effects. That might be useful for you looking at it in the cross village behavior.
Yeah, I'll look into that. Positive deviance.
Yeah.
That'd be a good search term for me. I mean,
Mhm.
we are we're very much interested in the knowledge that can be gained from natural experiments and quasi experiments. And I would say that we're relatively positive on that approach,
Mhm.
more so than say the folks at Jameel Poverty Action Lab.
Mhm.
But there are times when those kinds of observational studies can uh, cause you to infer an effect when there is actually a second
Mhm.
causal factor,
Mhm.
right? That, you can imagine how it might happen that the feeding the shrimps was ultimately due to let's say, more time available
Oh, yes, absolutely.
of the mothers, or some lurking hidden variable. So you do the best you can to untie
Mhm.
um, those causal models.
Mhm.
Yeah, but I think it's important to extract all the information you can
Absolutely.
from observational data, perhaps
Mhm.
before doing the experiments.
Yes, I agree. I'll stop here so that other people can ask. Sham, you wanted to ask,
Oh,
please?
I just wanted to mention, I think in your Bangladesh example, uh, I'm told that among European nations,
Mhm.
the average height of Dutch is the greatest.
Mhm.
So I asked the question about why that is the case.
Mhm.
And I was told that sometime in 1880s, the Dutch government instituted a program in which the expectant mothers received a home visit from a medical support person and advice on nutrition and care, health care for the mother and the fetus. And the results we can see within a generation or so, the height of the Dutch people. At least that's the story I'm told. I don't know. I have not verified it. Article.
I, I want to go back to one thing quickly. First of all, Sham is a co-conspirator in this collective. He's at Yale in the business school as a finance professor. And the thing I wanted to mention is in the positive deviance, they go deeper into the cultural practices and look for deviations from there and how to transfer it. So I think some of the hidden variables are probably taken care of by the depth of the study of the cultural practices and their blending. I don't think they are using any analytical methods. That's why I think there might be some ways we can think about. Anyway, I should stop. Sudhir, you want to say something, please?
Yeah. So thank you, Dan. One question I have is when we are looking at uh, analyzing the impact of interventions, you have talked about building a concept model or a conceptual model. What is the basis of that conceptual model? Is it with some of the available data on those interventions, or is it based on the general hypothesis kind of construction? What exactly is the basis for that?
Well, we do study the existing literature and mine out as much as we can, but a lot of it is based on the personal and professional experience of the actors in the room. So it's really a more informal kind of knowledge for the most part.
Okay. So then that becomes a basis for you to narrow down to the kind of data that you are going to collect, right?
Right. So by building that conceptual model, we are hoping to identify proximal observables that would help us to speed up our experimental efforts.
So where does this, like for example, once I narrow down to a certain model, what is the guidance that I can get from some of these statistical methods in deciding the samples that I need to look at?
Well, I think
does the model influence the samples sizes?
I think it can, because if you can pick a mediating variable that can be measured very precisely, then you don't need as many subjects, just as an example. But I have to say that if you have time to read a copy of Linda Collins' book, then you'll find there's a tremendous amount of detail. That's one of the great things about the MOST methodology. It is documented in great detail in this textbook. So you'll find there's an answer to the question that you posed, which is highly explicit and detailed.
Thank you.
Are there any other questions from the audience? Dan, I want to, given that we have a few minutes, I'm going to take you a little bit away from the lecture.
Okay.
From your perspective of having taught design and engineering at MIT for a long time and even produced a series of TV programs, what is your current thinking on the way engineering education should be done? What you have presented is one important method of trying to figure out what is the problem you are going to solve and how you are going to solve. Similarly, you have used different ways of teaching as well. So I thought we might take a few minutes from you on that.
Right. Thanks for asking that question. It's a really important one. I would say that I'm personally quite committed to the idea that engineers need to learn theory, to be sure, but they also need to be exposed to the ways that theory is used in a process that is not only analytic, but also incorporates synthetic activities, generation of new alternatives. And therefore, I always argue for more design experiences throughout the curriculum. I like to see some exposure in the first year, certainly a capstone, but preferably other experiences throughout all 4 years. And so that was an idea that was embedded into the Singapore University of Technology and Design, which was founded in collaboration with MIT. And they formalized it in this idea they called 4D. That means that there should be design within courses, design across courses, even within a term. So you learned how the multiple subjects that you were learning at a given time can be used together. Design across different years of the curriculum. So projects that might take a longer time and span multiple terms. And finally, also design that extends into the, let's say, informal curriculum, into clubs and teams and things that students are doing outside of the classroom. So I thought that represented a good answer and is, I think, a recommended practice.
And in your own experience at MIT, you have seen, I think you have been before you, and you especially have been using these courses. Do you see an effect on the student motivation and other aspects of the learning process?
I do. I mean, project-based design is difficult, right? It's hard to make sure that every experience is positive and motivating, and it won't always be, but a lot of effort goes into that at MIT, and I think that we're committed to it, that we believe that it's part of our charge. And in general, when you talk to people at MIT, they've really internalized that motto, mens et manus. It means something here. People really are committed to it.
Sudhir, you have any other comments from the educational direction from your side?
So I can share the similar experiences that we have gone through here in embedding design within an engineering program and blending both the elements of the industrial design and the engineering design right from the first year. So there are, it is challenging when you introduce that, and also what we experience is a different kind of students coming with a different kind of preparation, and a lot of work needs to be done before they become comfortable with dealing with the ambiguity that this whole process creates, right? And yeah, but definitely it is worth persisting, because that is the only way to rediscover that whatever elements of curiosity and so on among the students.
Dan, you have the last word, and then we can close the lecture for today.
Well, let me say thanks again for the opportunity to speak to you here over Zoom. I think the idea of focusing on innovation is really important, and you should stay committed to that. And I hope that if questions arise in the coming days, that you'll go ahead and reach out to me.
Thank you very much. Thank you for all the participants, all the people who attended the lecture. And we'll be in touch in 2 weeks' time. I believe I'm going to get a person who's going to talk about teaching ethics in engineering. I think that should be very interesting for us. I'll make sure to put the things up. Meanwhile, we have the recording. We will edit it and we are having some issues with YouTube. It's not letting me put more videos in my account. So we are trying to find other ways to put all these videos very soon. Thank you very much, Dan. Hopefully I'll see you this year sometime.